Saudi Arabia is one of the driest countries in the world, with more than 95% of its land covered by desert, almost no permanent rivers, and extremely low rainfall. Yet, amid this vast sea of sand, thousands of lush green circular fields have appeared, along with date farms, vegetable crops, livestock feed production, and even a modern dairy industry. To achieve this, Saudi Arabia has employed a wide range of technologies, including center pivot irrigation, drilling for ancient groundwater reserves, seawater desalination, rainwater harvesting, high-tech greenhouses, and soil improvement techniques for sandy land. But behind this remarkable achievement lies a major question. Is this the future of desert agriculture, or a massive gamble on water resources that are gradually running dry? Today, join Terran Works as we explore how Saudi Arabia transformed the desert into productive agricultural land. Since ancient times, the Arabian Peninsula has never been an easy land for agriculture. Most of Saudi Arabia's territory is made up of hot, arid deserts, where sand, rocks, and scorching sunlight dominate far more than fertile fields. Unlike the great civilizations that flourished along rivers such as the Nile, the Tigris, or the Euphrates, Saudi Arabia has almost no permanent rivers, receives very little rainfall, and possesses only limited arable land. As a result, for many centuries, life here revolved around nomadic living, oases, date palms, livestock herding, and a heavy dependence on the scarce underground water sources. This long history of scarcity made agriculture a matter of survival. When oil brought enormous financial resources in the 20th century, Saudi Arabia became determined to change the fate of its agricultural sector. The country began drilling for ancient groundwater, building center pivot irrigation systems, developing desalination technology, constructing high-tech greenhouses, and launching rainwater conservation projects, all with the goal of transforming the desert from a harsh landscape into part of a modern food economy. But to turn that ambition into real farmland, Saudi Arabia needed something even more important than oil wealth: water. On the surface, the country has almost no natural advantages for agriculture. There are no great rivers flowing across fertile plains, no abundant rainy seasons like those in tropical regions, and no moist soil sustained year-round. What people see instead are endless stretches of sand, rock, scorching heat, and land so dry it seems impossible to cultivate. Yet beneath that desert lies a hidden treasure. Fossil water aquifers accumulated thousands of years ago, back when the Arabian Peninsula was far wetter than it is today. With grasslands, vegetation, and heavy rains that once replenished the underground reserves. Saudi engineers drilled deep beneath the desert to pump this ancient water to the surface for growing wheat, vegetables, livestock feed, and supporting large-scale dairy production. But this is not a water source that can quickly regenerate. It is more like nature's savings account, built up over immense periods of time, yet capable of being depleted within just a few decades if overused. That is why the next challenge was not simply obtaining water, but using every drop as precisely and efficiently as possible. And that is where the center pivot irrigation system, invented by Frank Zabak from Colorado, became a critical tool that helped Saudi Arabia manage its precious water resources across vast desert farms. If viewed from above, the clearest symbol of Saudi Arabia's agriculture is the green circles scattered across the desert. Among the crops most closely associated with the center pivot irrigation system, wheat was once the most prominent. From the 1970s to the 1990s, Saudi Arabia used ancient groundwater reserves, deep wells, and massive rotating irrigation systems to transform sandy land into large-scale wheat fields. Each irrigation system rotated around a fixed pivot, spraying water evenly in a circular pattern, allowing wheat to receive sufficient moisture across vast, flat, and arid terrain. This system helped create a famous paradox. A country with almost no permanent rivers once managed to produce wheat on a massive scale in the middle of the desert. However, as groundwater resources were overexploited, the story began to change direction. Many of the circular fields gradually stopped producing wheat and were instead used to grow alfalfa, a nutrient-rich crop that is essential in the diet of dairy cattle. With alfalfa, the center pivot irrigation system continued to demonstrate its advantages. Water and fertilizers could be distributed evenly, helping the crop grow thick, green, and capable of multiple harvests each year. As a result, Saudi dairy farms gained a more stable supply of animal feed, even within a desert environment. Nevertheless, alfalfa is also a highly water-intensive crop, so each green circle not only represents the ability to conquer the desert through technology, but also raises an important question about the true cost of agriculture in a water-scarce nation. But if ancient groundwater reserves could eventually run dry, Saudi Arabia needed a more sustainable path forward, preserving the water that falls today. In the Al-Baida region of western Saudi Arabia, the land had become severely degraded due to overgrazing. When Bedouin communities were forced to settle permanently in one place, livestock continuously grazed the same areas, causing vegetation to disappear, soil to become compacted, and rainwater to stop soaking into the ground. Instead, the water rushed across the surface, carrying away fertile topsoil. To restore the area, a project was launched with the participation of Neil Spackman and Mona Hamdi. They built stone terraces, small check dams, and shallow trenches designed to slow the flow of rainwater. When the water no longer rushed directly to the sea, it began seeping back into the soil, trapping sediment, seeds, and moisture that allowed drought-resistant plants to grow. Although the project struggled for years because of limited funding and drought conditions, by 2018-2019, when rainfall finally returned, the water retention system proved effective. The area gradually turned green again, resembling a savanna landscape. After learning how to retain rainwater on land, Saudi Arabia also had to turn to a far greater water source, the sea. The country lies alongside the Red Sea and the Persian Gulf, but seawater cannot be used directly for agriculture or daily life because of its high salt content. As a result, desalination became one of the key pillars of Saudi Arabia's water strategy. In general, there are two common methods for turning seawater into fresh water. The first is thermal desalination, which uses energy to evaporate water and then condense it, leaving the salt behind. The second is reverse osmosis, which uses pressure to force seawater through specialized membranes that trap salt and impurities. But the challenge is that desalination requires enormous amounts of energy. In other words, the water problem quickly becomes an electricity problem. To green the desert, you need water. To obtain water in an arid nation, you need desalination. And to desalinate at a large scale, you need stable, affordable, and lower-emission energy sources. That is why the future of Saudi agriculture cannot be separated from the country's energy strategy. Still, desalination is not a magic solution. It is expensive, requires massive infrastructure, and demands careful treatment of the concentrated brine waste it produces. But when combined with water-efficient irrigation, water recycling, and land restoration efforts, it can become an important part of the journey to transform the desert into habitable and productive land. But if desalination is expensive, requiring massive plants, water pipelines, pumping systems, electrical grids, and long-term operating costs, then the next question is, where does Saudi Arabia get the money to pursue this ambition? The answer lies in the very resource that transformed the kingdom's destiny during the 20th century: oil. For decades, the enormous revenues generated by the oil and gas industry enabled Saudi Arabia to build cities, highways, seaports, power plants, and now even large-scale water projects. In other words, oil not only created wealth, but also became the source of capital that Saudi Arabia could invest in building a future less dependent on oil itself. This paradox is what makes the story so remarkable. A nation using money from fossil fuels to finance desalination plants, irrigation systems, agricultural research, and land restoration projects for barren environments. From deep beneath the ground, Saudi Arabia pumps oil to generate financial power, then uses that financial power to find water, preserve water, and gradually transform the desert into land capable of sustaining human life. But as Saudi Arabia expanded agriculture in the desert, it increasingly faced an unavoidable limit. Groundwater cannot be extracted forever. The fossil water aquifers deep underground once enabled the kingdom's wheat boom and its green fields, but they are not replenished as quickly as rainwater or rivers. If extraction continues at high rates, today's greenery could become tomorrow's crisis. As a result, Saudi Arabia began considering a different strategy, moving part of its agriculture beyond its own borders. Instead of trying to grow everything in an arid land at any cost, it invested in and acquired farmland in more favorable regions, such as the United States, Argentina, Indonesia, and several African countries. This form of offshore agriculture allows food to be produced outside the country while still keeping supply chains under strategic control. However, this approach also reveals a clear reality. If Saudi Arabia wants to revive its own desert, it cannot rely solely on drawing from ancient water reserves. It must also learn how to preserve the water of the present. But for desert agriculture to survive beyond just a few decades, Saudi Arabia needs more than groundwater and desalination. First and foremost, water is inseparable from energy. Desalination plants, pumping systems, and irrigation networks all require stable electricity supplies, meaning the future of Saudi agriculture is closely tied to the kingdom's long-term energy strategy. At the same time, urban and industrial wastewater can also become a valuable resource if treated properly. In an arid country, every cubic meter of recycled water used for irrigation is one less cubic meter of groundwater that must be pumped from beneath the earth. Another important piece of the puzzle is liquid nanoclay, or LNC. This technology coats sand particles with a clay-like layer that helps the soil retain moisture more effectively. If desert sand behaves like a sieve that lets water pass through too quickly, LNC aims to transform it into something more like a thin sponge around plant roots. As a result, the future of greening Saudi Arabia may not depend on a single breakthrough solution, but rather on the combination of energy innovation, water recycling, soil improvement, and smarter resource management. But the future of Saudi agriculture may not lie solely in vast open fields across the desert. For crops that require a more stable environment, such as tomatoes and cucumbers, Saudi Arabia is experimenting with a different approach, moving cultivation into high-tech greenhouses where temperature, humidity, light, and water usage are all carefully controlled. These are two crops with high consumer demand, strong commercial value, and excellent suitability for closed-environment farming systems. What makes this model especially notable is that some technologies can utilize seawater or brackish water to cool the greenhouses, while also reducing the amount of fresh water needed for cultivation. For tomatoes, a controlled environment allows the plants to produce fruit more consistently, lowers the risks caused by extreme temperatures, and ensures more stable year-round yields. For cucumbers, greenhouses help maintain the proper humidity, temperature, and irrigation conditions, enabling rapid growth while still conserving water. If the circular fields once symbolized an era in which Saudi Arabia relied on groundwater to expand agriculture, then the greenhouses growing tomatoes and cucumbers may represent a new phase. Not an attempt to turn the entire desert into farmland, but the creation of smaller, more precise production zones that depend far less on scarce freshwater resources. From the ancient groundwater layers deep beneath the earth, to the green circular fields visible from space, to desalination plants and rainwater harvesting projects like Al-Baida, Saudi Arabia is showing that the desert is not entirely a lifeless land. But this story also leaves a very clear reminder. Greening the land is not achieved by money, machinery, or massive pipelines alone. It depends on how humans understand and manage every single drop of water. If fossil water is overexploited, today's miracle could become tomorrow's crisis. But if rainwater is captured wisely, wastewater is reused, sandy soils are improved, and technologies are combined intelligently, even arid lands still have a chance to recover. Covering more than 2.1 million square kilometers, nearly 3 times the size of Texas. Yet more than 37 million people in Saudi Arabia can only remain concentrated along the 2 coastlines of the Red Sea and the Persian Gulf. where the country's major cities, strategic ports, and nearly all of its most important economic infrastructure are located. In many areas, average annual rainfall is below 100 millimeters, while summer temperatures frequently exceed 45 degrees Celsius. Under such harsh conditions, rivers are almost non-existent, surface water has nearly disappeared, and underground aquifers remain under constant extraction pressure. And that is Saudi Arabia's greatest paradox. This country possesses what the world desires most, oil. But what it lacks is water. Despite holding more than 260 billion barrels of oil beneath the ground, it still has to spend billions of dollars just to create every drop of fresh water. In the Middle East, oil built empires, but water is what determines which nation can survive in the long term. To overcome that limit, they built a nationwide water system consisting of tens of thousands of kilometers of high-pressure steel pipelines and one of the largest booster pumping networks in the world. But where does the true lifeline of this machine come from? The answer lies just offshore: the sea. Seawater contains about 3.5% salt, far too salty for drinking or irrigation. So nearly 16 billion liters of seawater are treated every day at giant coastal plants, then pumped deep inland to sustain modern cities, massive industrial zones, and lands that nature never intended for human settlement. But to push water thousands of kilometers across one of the harshest deserts on Earth, Saudi Arabia first had to build rivers made of steel. Everything begins with the very weapon that will carry seawater across the desert: steel pipelines. To withstand constant high pumping pressure, impact during underground installation, and extreme desert temperatures, these pipelines typically use high-strength carbon steel, a material widely used in the oil and gas industry. The process begins with massive rectangular steel plates, pre-cut to precisely calculated dimensions. Each plate is large enough that once rolled, it forms a pipeline with a diameter of around 1.8 meters and a wall thickness of nearly 25 millimeters. The steel is then fed into a multi-roll forming system. Industrial rollers gradually press and bend the plate until the flat sheet becomes a complete cylinder. Once the two steel edges meet, the pipe shell is ready for the most critical stage: longitudinal seam welding. Here, automated welding robots travel along the full length of the pipe, creating a joint strong enough to withstand continuous water pressure for many years. After welding, the pipe is cooled with water, precision ground to remove burrs, and correct tolerances before both ends are beveled to standard specifications, so field connections can be faster, tighter, and more resistant to pressure. But finishing the pipe is only the first step. The next challenge is transporting these steel giants, each weighing dozens of tons, across one of the harshest environments on Earth. At staging yards, each batch of pipes is coated and arranged in the exact installation sequence to prevent delays once field construction begins. Each pipe section is typically around 12 meters long and weighs up to 40 tons. Long enough to reduce the total number of weld joints across the line, yet still within the limits for loading onto specialized heavy transport vehicles and moving by road. A single 1,000-kilometer route alone requires more than 80,000 pipe sections, turning logistics into a massive industrial campaign. But the greater challenge lies in the route itself. Saudi Arabia cannot simply draw a straight line across the desert and start digging. Engineers must use high-precision GPS, topographic surveys, and terrain scanning to determine the most efficient path across thousands of kilometers of sand and rock. Once every final coordinate is locked in, an invisible road begins to appear across the desert. First, the entire surface along the route is leveled and widened into a corridor about 40 meters wide, stretching for hundreds of kilometers. A massive construction site reaching all the way to the horizon. Next, heavy excavators begin digging trenches according to the exact designed elevation. Depth typically ranges from 2 to 3 meters, enough to protect the pipeline from surface heat, vehicle loads, and external environmental impact. But the desert is not only sand. Many areas consist of hard rock or semi-mountainous terrain where standard excavator buckets are nearly useless. In these zones, construction teams must drill holes, place industrial explosives, and break rock through controlled blasting phases to clear a path for the pipeline. Once the trench is complete, sharp rocks and uneven ground still make immediate pipe placement impossible. A bedding layer of fine sand or granular material is spread along the trench bottom to create an even cushioned surface, reduce localized pressure points, and limit stress on the pipe body throughout decades of operation. Once the trench is ready, the next challenge is turning tens of thousands of separate steel sections into one continuous pipeline stretching thousands of kilometers. This is where construction speed must move together with absolute precision. Each pipe section is lifted into position by cranes. Before welding begins, a 360-degree hydraulic internal clamp is inserted inside the pipe to align both ends perfectly and maintain exact concentricity. Even a minor deviation can create flow turbulence, increase stress, and shorten the lifespan of the entire line. Once both ends are secured, an automated welding system begins traveling around the circumference of the joint. But speed means nothing if the weld is not flawless. That is why every connection is then inspected using industrial ultrasonic testing to detect hidden cracks, voids, or defects invisible to the naked eye. After inspection, the joint area is coated with multi-component epoxy to restore corrosion protection for the decades ahead. Only then do tracked side boom machines move along the worksite, lifting the entire steel string with wide slings before lowering it into the trench centimeter by centimeter to prevent bending or damage to the protective coating. The final stage is multi-layer backfilling. Fine sand is placed first to protect the pipe surface, followed by soil and rock added in compacted layers, gradually burying the entire steel river beneath the desert to keep it stable for decades. But even at this point, Saudi Arabia has only finished building the road. It still has not created the water. Bringing water from the sea deep into the interior is already an astonishing engineering achievement, but turning salt water into fresh water suitable for drinking, agriculture, and industry is what truly earned Saudi Arabia global respect. Everything begins in the vast deep blue ocean offshore, seemingly endless in scale. Instead of drawing water close to shore where sand, oil, plankton, and pollution are more common, plants usually place offshore intakes hundreds of meters to several kilometers from land, where deeper water is more stable. Intake pipelines measuring up to 2 to 4 meters in diameter continuously pull seawater to shore, and a single major intake point can process 50 to more than 100 million liters per day. Once inside the plant, seawater first passes through coarse screens, metal barriers that stop unwanted visitors, such as seaweed, floating plastic, wood debris, and larger marine life. But blocking large debris is not enough. Fine screens are installed behind them to capture smaller fragments, juvenile fish, shells, and remaining organic matter before the water moves deeper into the treatment system. But the most dangerous part is nearly invisible. Seawater still contains fine sand, silt, and countless microscopic suspended particles that can wear down pumps and destroy expensive membranes further downstream. For that reason, the water is sent through multi-layer sand filtration, where it percolates through sand beds and filter media that gradually trap impurities. After this stage, turbidity often falls from 5 to 20 NTU to below 1 NTU. Next comes chemical treatment. Sodium hypochlorite is injected for disinfection and to control biological growth inside the system, while ferric chloride helps gather ultrafine particles still suspended in the water. Once their surface charges are neutralized, they bind together into larger clusters called flocks, heavy enough to settle to the bottom of tanks along with many attached contaminants. But the water is still not clean enough for the most expensive component in the entire plant, the RO membranes. So the flow continues through cartridge filters with pore sizes of only 1 to 5 microns, the final defensive layer protecting membranes worth millions of dollars from clogging or premature damage. Then the water reaches the heart of the entire system. Reverse osmosis. In nature, if fresh water and salt water are separated by a semi-permeable membrane, water naturally moves toward the saltier side to balance concentration. That is osmosis. Saudi Arabia does the opposite. Giant pumps generate pressures of around 55 to 70 bar, equal to many times the pressure inside a car tire, forcing seawater against the laws of nature through ultrafine polymer membranes. The membrane surface contains filtration openings at the molecular scale. Water molecules can pass through, but most dissolved salts, bacteria, heavy metals, and impurities are blocked. As a result, the system splits into two streams. One is permeate, purified fresh water. The other is brine, concentrated salt water carrying nearly all removed contaminants. But maintaining a constant pressure of 60 bar requires enormous electricity demand. That is why modern complexes use energy recovery devices to capture remaining pressure from the brine stream and transfer it back to incoming feedwater. This technology significantly cuts power consumption, turning desalination from an overly expensive process into something viable at national scale. Many complexes also use second-pass RO, sending permeate through another membrane stage to reduce conductivity, lower boron levels, or meet higher industrial and drinking standards. But water that is too pure cannot be used directly. It lacks calcium and magnesium and can become aggressive, meaning it more easily corrodes metal pipelines. That is why the final stage is remineralization. Here, water passes through limestone or receives controlled mineral dosing, while pH and alkalinity are adjusted for chemical stability. After this step, the water is not only clean, but also suitable for circulation through a massive steel network and safe for millions of people to use every day. That entire treatment chain runs continuously, 24 hours a day, 7 days a week. And Saudi Arabia does this at extraordinary scale, nearly 16 billion liters of seawater every day, placing it among the largest desalination capacities on Earth. But producing fresh water solves only half the problem. Now they must push it thousands of kilometers across the desert every single day without interruption. That is why booster stations appear along the entire route, giant pressure-boosting facilities that push the water forward whenever pressure drops after long distances. At the end of those pipelines stand inland cities such as Riyadh, where millions of residents, hospitals, industrial zones, and the entire rhythm of urban life depend directly on a river flowing beneath billions of tons of sand every day. In a land where nature provided no water, Saudi Arabia built rivers of its own. While Saudi Arabia chose to turn the sea into fresh water and pump it across the desert, another nation used billions of liters of seawater to revive the destiny of an entire country.